My name's Chris Wilkins. I'm the CEO here at LEAF. We are a UNSW founded company, originally started in 2016, and we're based in Mona Vale in Sydney. And we're part of the Future Food Systems CRC in two different projects, which I'll talk a bit about today, as well as what we've been up to as a company. We do things that look like this in the bottom left-hand corner, a bright red luminescent greenhouse. But before we can sort of unpack what's going on here, we need to take a moment to think about sunlight. And what is sunlight? So rainbow is quite a good lens to look at it through. We have these packets of energy called photons that rain down on Earth to us and bounce off things or become absorbed by things. And it really is the source of all energy on Earth. So incredibly important. And what we do as humans is we make sense of the world around us by the color of the light that bounces into our eyes. So it's easy to forget this. We probably all intuitively know it, but if we take a minute to think about that, our eyes are a lot like camera lenses. And we have these different photons with different amounts of energy, and that amount of energy dictates what color the photon is. So at one end of the spectrum there, you can see blue light, which is a high energy photon, and at the other end you have red light, which is a lower energy photon. Beyond that spectrum, you have the non-visible part to the human eye. So at one end you have UV light, which gives us a sunburn, and far red and onto infrared light, which makes us feel warm. So at LEAF, we're engineering that sunlight spectrum for the horticulture industry. And this is a relatively well-known field, actually. The LED industry, particularly companies like Philips, who have spent a huge amount of time developing energy efficient lighting. So what that means is they're just producing less light, but they're producing targeted wavelengths of light. So plants are green because they reflect a lot of green light. They're not very good at absorbing that green light, but it bounces off their leaves and into our eyes, and then we see them and they're green. So knowing that, Philips are able to design LEDs which produce just the color of light that plants want in order to photosynthesize efficiently. So it's much cheaper for the electricity bill for an indoor farm if you can use LEDs rather than, say, an incandescent or a fluorescent light. Now, sunlight contains roughly equal amounts of all different parts of the spectrum. And at LEAF, what we're doing is shaping that spectrum to be more similar to an LED. So it's an improved quality of sunlight that the plants can photosynthesize more efficiently. It is not a filter. This is probably one of the most common misconceptions that we get. We are not reducing the light levels. Well, there is a net reduction, but we are increasing the amount of red light. So similar to an LED, which has less light, it has a higher quality of light. So here you can see it's a shift from green light, which is absorbed by the film. The film becomes charged up, and then it emits red light, like an LED emits red light. So there's a net increase, and that's a net increase compared to direct sunlight. So if you put a piece of leaf film and compared the red light underneath the leaf film compared to direct sunlight, you'd see about a 10 to 15% increase in the total amount of red light being measured by the spectrometer. This is called a Stokes shift, moving the wavelengths from that higher energy green but lower value to the lower energy red but higher value. You do see a reduction in blue light and green light in this graph, and that's a function of reflection. So blue light has a tendency to bounce off things. It will be reduced if it goes through glass or just conventional clear poly greenhouse film. Then we also have diffusion, which is really important. It's the scattering of light around the greenhouse. So you can imagine a plant gets a lot of light on top of the plant, but very little in the shadows underneath the leaves. But if you can diffuse light, you can bring light down underneath the canopy, and more of the plant can photosynthesize, and it evens out the intensity. So rather than burning the top and shading the bottom, you can get a nice, even, uniform light print throughout the greenhouse. As a company, we are really focused on chemical engineering. We produce a luminescent dye, which is the core technology. From that point, we produce a master batch. And this is essentially the blending of dye with plastic and creating a very, very concentrated plastic pellet. And that's kind of the tricky part. Once that's done, that plastic pellet master batch can be sent out to pretty much any extrusion company which works with that type of plastic. So we work with polycarbonate at the moment. So we can send that polycarbonate out. They can mix it in with clear polycarbonate, and then they can extrude products that they would normally make. So for us, in this case, it is a film that is installed in a greenhouse. The film comes in 1 meter wide rolls, 100 meters long, and it's got the size by a very skilled team and installed on the inside or the outside of a glass house. And once that installation is complete, you have, like you can see in the top right-hand corner, a spectrum optimized glass house where all of the light that enters the glass house has transmitted through the film, and it's well distributed throughout the space. Like I mentioned at the start, we're involved in two projects through the Future Food Systems CRC, the Glasshouse Films project out at Richmond at the National Vegetable Protected Cropping Centre, which Sachin is involved in, and the Blueberry Nutritional Optimisation Trial, which Richard and Garima will talk about a bit later. So at Richmond in the NVPCC, we're using the LLEAF 620 nanometer red film. And we're predominantly interested in what effect does this film have in a glasshouse environment on the yield in terms of the quantity and the quality of the yield. There's also been some measurement regarding light transmission captured by spectrometers, but primarily we're there to answer the question, how much more do you get, and is that produce of a better quality? With the Blueberry Nutritional Optimization Trial, it's involving two of our films, the red one, the same red one, and a 660 nanometer film, which appears purple, but it's actually emitting far red light. So it is luminescent, just like you see the bright red one, but it's luminescent beyond what our eyes can perceive. So it appears purple because that's what's left for our eyes to see. And that's particularly interesting for the secondary metabolites. So we're talking about things like flavonoids, antioxidants. And I know that Richards and Garima have got more to talk about UV and the effect that it has on plants like blueberries. Beyond that, there's also been a bit of looking at the dye, what's the absorption properties of our dyes, the material sciences, and other products on the market which also shift the color of light, known as color conversion film. So very interesting research has been particularly useful for us. On that note, I guess, starting with the Future Food CRC, you imagine it's about validation. So it's very hard to go to a large commercial glasshouse, which is many hectares in size, and convince them to install a basically untested product. So having a smaller glasshouse with controlled chambers where you can do side-by-side experiment gives the grower confidence that they can buy the product that's going to work for them. So the validation of this core principle, additional red light, targets photosynthesis, improves the yield of the plant. Getting that done independently by a university is incredibly important. And I guess that was sort of the overarching reason that we wanted to join the CRC. Being part of the CRC, it's been much more than that. So working with Goran, the facility manager, and Norbert, who have been working hands-on with the film, cutting it to size and figuring out how do you actually install it. Every glasshouse is different, every greenhouse is different. We get this question from customers all the time. So having a facility where we're engaged in that process, and it's not them coming to us going, how do we install it? It's them figuring out how do we install it. And that's actually incredibly valuable feedback from a product point of view. Then throughout the research, there is the generation of new knowledge, asking better questions, things we didn't know that we would need to figure out along the way. And yeah, lastly, which is just as important as the other points, is the marketing benefit that comes with it. So being able to bring a customer out there and for them to see with their own eyes, what does it look like? For them to be able to talk to the researchers, what has been your experience with it, has been absolutely critical for LLEAF's success. In the bottom left, you see ABC Landline came out and filmed a story in the glass house. And with reporter Sean Murphy, I was able to walk around in the facility, talk about the research that's being done, and he was able to interview Sachin and some of the other researchers while he was out there. So exposure for an early stage startup is just absolutely critical. So that's been one of the benefits that we didn't necessarily think about, but has been very important. In terms of our product development thus far, over the course of the CRC, we've gone through 3 generations of LLEAF film. So starting out with a rather thick film, 400 microns, so just a bit thinner than half the thickness, half a millimeter, down to a generation 2 film, which is 250 microns, so going nearly half the thickness. Very important for light transmission. We're able to play around with surface texturings, as well as getting a higher performance out of the die, so a greater shift. So looking around the sort of the 20-30% increase in the amount of red light that's coming out. And then moving on to a generation 3 film at 50 microns, so half the thickness of a sheet of paper. And then again, also being able to see an increase in the shifting ability and the performance of the die. What's coming next is very exciting and what we're currently working on at LLEAF. So last year and a lot of this year, we spent time out in the market talking to growers in the Netherlands, greenhouse builders, trying to sell our product. And that's a very important step for a startup. You go out with your minimum viable product and you try to figure out what the barriers are to large-scale adoption in the market. And we have been able to sell quite a bit of product, but a lot of it really is for that research and trialing purposes. The number one feedback was it is too expensive. It is a difficult material to make, particularly in polycarbonate. It requires precision equipment that only exists in some countries and is very expensive equipment. So that was one big lesson from last year was make it cheaper. And the other lesson was make it bigger. So we make a 1 meter wide roll of polycarbonate. Nobody in the industry buys a 1 meter wide roll of polycarbonate. So embedding the technology into product that the industry is already buying that's probably the biggest lesson. So now we're building a low cost film. Pictured in the bottom right is a concept there of a polyethylene film that you can just wrap a greenhouse in. That's what the industry is currently using for low and medium tech structures. You can blow that film 10 meters, 12 meters wide, and it's an addition of technology to an existing product that the market's already buying. With that comes a massive reduction in cost. We're probably by about 10-fold reduction in cost. So that is an absolute game changer for us and for the industry's ability to buy the product. We're also developing a climate screen. So climate screens are a horizontal curtain that is used in pretty much all high-tech and most medium-tech greenhouses. It's a breathable material. It's a netting that is run on wires and motors, and it's pulled across a greenhouse when the sunlight is too intense and used to reduce the intensity of light, but also to trap heat above the climate screen for recirculation later. So this is a really neat application of our film because you can bring it across just when you need it. So in the morning and afternoon, you have it open. You don't use it in the midday sun. You make the most of that really high intensity sunlight. Pictured in the middle there is an agrivoltaic a photo of an agrivoltaic project we're working on. Now, this is really the future. It's still early days. There's not a lot in this space, but the combination of generating electricity instead of just shading plants, but let's not reflect light that could be turned into electricity, particularly when the sun's shining and heating and ventilation and cooling systems need to be run. So turning electricity on site, greenhouses will need to become more energy efficient. That's a trend that we see very much in Europe at the moment with the cost of electricity. So integrating solar panels into greenhouses. And our project there is to make a complementary panel that goes in between solar panels. They're on motors, they move around, they get out of the way of the sunlight when you want it and in the way of the sunlight when you don't. And our panels reflect light into the solar panel and transmit light down to the plants selectively. And then, of course, the development of new dyes. So LLEAF as a company being focused on sunlight engineering, means we stay close to the problem. So that could be looking at, can we shift the seasonality of plants? Can we make plants fruit and flower out of season by using far red shifted dyes? Or can we address the amount of heat that comes into a greenhouse, particularly important in regions like the Middle East? So continuing to innovate in the space and develop some new dyes. In terms of market expansion, we have been well supported by Investment New South Wales through two of their Going Global programs, one to the UAE and one to the UK. Pictured in the bottom right there is an interesting business that I visited while in the UK. They're growing bok choy in vertical towers. And it's a very high density, it's a lot of plants, and there are challenges there around getting the sunlight down in between those towers to the bottom. So crop uniformity. It's not all about just increasing the yield, but sometimes a grower has a problem where the plants at the bottom are too small and the plants at the top are much, much bigger. So how do we disperse light more efficiently? How do we move light down to lower crops? And really deal with all challenges that come up around sunlight in protected cropping. Um, we've also been attending Green Tech Amsterdam for 3 years in a row now. And we're pictured there is our partner from Wilkins Deutschland, the largest distributor of polycarbonate films, where we co-exhibit. And this is one of the largest exhibitions in the protected cropping industry. And just connecting with all those industry partners who are building greenhouses or sourcing greenhouses. I mentioned before about the agri-voltaic project. This is called the Go Green Co-Innovation Program. So funded by the Department of Foreign Affairs and Trade. It's a program designed to foster collaboration between Australia and Singapore. And we have a partner in Singapore that handles a lot of that PV and motorized part of the system, so we can focus on the sunlight engineering through our panels. Lastly, it's raising capital. So we've been fortunate to raise 2 rounds of investment capital. We have investors from Denmark who are climate change focused investors who see LEAF film as a great way to increase food supply without pouring more electricity into LEDs. So we're now in the process of raising additional capital in a Series A round. That is the end of the presentation. Thank you.